Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is a lecture for intermediate algebra on quadratic applications. So prior to viewing this lecture, you should have spent some time going through some lectures, getting familiarized with quadratic equations and graphs, specifically graphs of quadratics, because that's how I solve all my quadratic applications, or almost all of them. There are generally two types of quadratic applications. There are those that they handed you an equation and you have to figure out when this equation is maximized or minimized. And then there are the rest, which are those where you're not given an equation, instead you're given a situation. And in these, there's usually some type of overriding formula that you have to remember. It could be a revenue formula. It might be some type of distance equals rate times time type of formula. We'll work with both of these applications in this lecture. The first example is one in which somebody's given us an actual equation. I might have to rewrite this equation just so that it's understandable. Otherwise, it might be a little difficult for you to kind of see. So let me write the equation as h is equal to negative 16 t squared plus v naught t plus s naught. Ignore this notation there if you haven't seen function notation. It's just a new notation, but don't worry about it for now. All right, recall that a projectile with initial height s naught, so that's the initial height, and initial velocity v naught has a height at time t of h, which equals a negative 16 t squared plus v naught t plus s naught. And by the way, that notation is called v naught, or v sub 0, some people call it. If a ball is tossed upward with a velocity of 64 feet per second from a height of 5 feet, then what is the maximum height reached by the ball? Okay, so we've read the problem. I'm just going to go through the problem solving process here. We've read the problem. I understand the situation. Somebody's tossing a ball up in the air, and we want to know when it's at its maximized height. Normally we would label unknowns, but actually they've already labeled all of our unknowns. They've told us, in fact, what our v naught, our initial velocity, is. They say the ball is tossed upward with a velocity of 64 feet per second. Feet per second. Okay. And then they say it's tossed from a height, an initial height, s sub 0, of 5 feet. Perfect. And so the next step is usually to write an equation, but they've actually given us an equation, so I will use all this data in our equation here. I'll do a little substitution. H is equal to negative 16 t squared plus 64 t plus 5. And we want to know, when is the height of the ball maximized? Now, if you think about this equation, this is a parabolic or a quadratic equation which has a parabolic look to it. Looks like that, and I know it looks like it opens down because there's a negative on my lead coefficient. That always means that the parabola opens down. So I know I'm going to have some type of maximum value. Now, everybody has a different method for doing this. Some people memorize some type of formula, whatever, but I will tell you right now, I always graph to find maximum or minimum values. I always graph just because I would like to have practice. So let me open up a new page here, and we want to maximize the graph of this parabola, or the graph of this quadratic. So the first thing I'm going to do is graph it, actually. And recall my method for graphing. I just want to know when we hit the vertical axis. So I want to know the h-intercept. And that happens when t is 0. So if you let t equal 0 in this equation, you'll get that h is equal to 5. Which makes sense. It's saying that initially the height of the ball is 5, which is exactly what it is initially. And now I want to know, when am I at that height again? In other words, I know the ball is going to arc up and come back down. The question is, when is it going to be exactly at a height of 5 again? So I'll write that down. I know this is going to happen because it's a parabola and they're symmetric and they have that climb and fall thing going on. So I'll let h equal 5 in our equation. So we get 5 is equal to a negative 16 t squared plus 64 t plus 5. And now I see I could start to solve this by subtracting 5 from both sides. So this implies that 0 is equal to a negative 16t squared plus 64t, and the 5 is gone. And again, I can continue to solve this by noticing that both of these terms have a 16t in common. So I'll factor that out. In fact, a negative 16t I can even factor out. I'll be left with a t minus 4. So therefore, I have two objects multiplying to become 0, means either the first one is 0 or the second one is 0. In other words, the height is 5 again when t is equal to either 0 or t is equal to 4. And we already have it labeled for t equals 0. When t equals 0, the height is 5. So this must be t equals 4. The height is 5. And halfway in between is the axis of symmetry. And you know what? That's all we really need to know. Axis of symmetry occurs at t equals 2. Now remember what the question is asking, so let's hop back to the question. It says, what is the maximum height reached by the ball? Okay, I guess we do need to know a little bit more. What is the maximum height reached by the ball? Sometimes you have to pay attention to the question because sometimes they say, when does the ball reach its maximum height? It reaches its maximum height at 2 seconds. And if that's all they were asking, well then I'd be happy and I'd be done. But unfortunately, they want a little bit more. So let's go ahead and plug in 2 for t in our equation there. So let's see, h is equal to a negative 16 times 2 squared plus 64 times 2 plus 5. So let's see what we have here. That's going to be a negative 16 times 4, or in other words, a negative 64, plus 128 plus 5. That's going to be a 69, I think. Yeah, I think that's 69. So it tells me that at a height of 69, we have our maximum. Let me go ahead and plot that on here so you can see it. Unfortunately, if that's 5, this would be 10, 15, 20, 25, 30, 35, 40. It's way up there. So I'm just going to pretend it's right here for now. Not that it's that important because they're not really asking me to graph it, but that apex occurs at 2,69. So now when you're done doing all the computations, you should always, well, technically the 5th step for a problem solving process is to solve, and the 6th step is to state the conclusion. And here we're going to go ahead and state our conclusion as being the ball attains a maximum height of 69 feet. Now these are the easier problems because they give you an actual equation, but the idea still is the same, that what you're going to do is find a couple symmetric points halfway in between them in this vertex in the axis of symmetry. Now let's try some problems that are not so easy. In fact, problems where they don't give us equations at all. Now to illustrate the idea of a problem I'm about to do, it's a very common maximization problem that occurs usually in most math textbooks, where you have a fence built up against a barn or a river or something like that. In this case, you can see a top-down view right here of a fence being built up against a barn, and a side view as well. And as you adjust the width of this, you have to sacrifice some length to the fence. You only have a certain amount of fence, basically 200 meters of fencing available. So if you add some width here, you'll steal from the length. So watch as I manipulate this. I'm adding to the width, so I have to steal from the length. And you can see what happens with the picture, and you can also see this graph right here represents the area. So if I have a fence, if I build, I'm sorry, a region where the width is extremely small, 1 meter, but the length is 198 meters, well, I've used 200 meters of fencing, right? 1 meter here, 198 meters there, and another 1 meter up against this fence, so that's 200 meters. But the area is so small that we can't fit anything in there, and it's a very small area. But as I increase the width, you see by the parabola right here that represents the area, there's a point where I get a maximum area. And that's what we're normally concerned with, finding that maximum area. And if you go beyond that point, you start minimizing your area again, or reducing your area. Okay, that being said, let's try a problem like this algebraically. American River College has plans to construct a rectangular parking lot on land bordered on one side by a highway. There's 640 feet, or maybe I should say there is 640 feet of fencing available to fence the 3 other sides. What dimensions would maximize this parking lot? And so let's go ahead and draw a picture of this. I've read the problem, I understand what's going on, and a picture would really help. So let me go ahead and quickly jot down a picture. The green will represent the highway that the fence is being bordered up on. And let's go ahead and call this dimension W for the width. So this must be W as well. We'll call this dimension L for the length. I happen to know that at this point that we've read, we understand. The next thing we need to do is label our unknowns. And we've actually done that. W is the width, L is the length. And now the fourth thing you need to do is write equations. So essentially what you want to do is, since you have 2 unknowns, you'll need 2 equations. One of the equations I'm going to get, since we have 640 feet of fencing available, I happen to know that W plus L plus W should equal 640. In other words, 2W plus L should equal 640. The second equation is actually going to come from this last sentence. What dimensions would maximize this parking lot? In other words, maximize the size or the area of this parking lot. So I want an equation for the area of this parking lot. Area is going to equal length times width. That's just a rectangular area. And what we're going to do is, because we're being asked to maximize this, you always keep the variable you want to maximize. So I wrote that down there. Always work with and keep the variable you want to maximize or minimize. So this equation is going to be the equation I work with here, but there's a problem. I have too many variables in that equation. So what I'm going to do is I'm going to take a look at this equation right here and solve it for L. So I'll subtract 2W from both sides and essentially get something like L is equal to 640 minus 2W. And that's so that we can write this second equation in terms of really 2 variables. A is equal to, instead of L, I'm going to replace it with 640 minus 2W. And you can see, okay, that's like a quadratic function or a quadratic equation, honestly. Remember, a quadratic equation looks something like y is equal to ax squared plus bx plus c. And if you think about it, there's only 2 variables here, x's and y's. Well, there's only 2 variables in this equation as well, w's and a's. A is playing the role of our y variable, and w is playing the role of our x variable. Since we want to maximize this area, I'm going to graph this. Now before I do, I want to draw your attention to something here. Whenever you're working with applications and where you have to create the equations, you're almost always going to get a factored equation like this. Notice this is factored. We want to take advantage of that. You spend so much time in mathematics learning how to factor things, that type of thing, that if somebody hands you something, or if you happen to accidentally create an equation that's already factored, leave it factored. Use it. How are you going to use it in this situation? Well, you're going to stray a little bit from what I have taught you to do. Normally when you graph a quadratic, I say find the vertical intercept and find its symmetric points. Well, in this case, since it's already factored, it's actually pretty easy to find the horizontal intercept. So if I find the horizontal intercepts, I promise you that will result in symmetric points. And halfway in between those horizontal intercepts will be the axis of symmetry. So let's go ahead and find out, how would you normally find an x-intercept, which is a horizontal intercept? The way that occurs is you would let the output, or y, or in this case a, be 0. So we're going to let a equal 0. If you do that, you get 0 is equal to 640 minus 2w times w. And this is beautiful because this tells me the area is 0 when w is 0 or when w is 320. So let me plot those on here. The area is 0, in other words, I'm at a height of 0 when my width is 0 or when my width is 320. Halfway between these 2 points is going to be the axis of symmetry, because the fact is I know this is going to be a parabola. I know it's going to be a parabola because this is like a equals something with a w squared. That's got to be a quadratic equation. So halfway in between, I'll mark this axis of symmetry. Halfway in between those two is going to be w equals, let's see, 150, 160. So I know I'm going to have a parabola that attains its maximum right halfway in between at 160 for w. Now let's read this question again. What dimensions would maximize this parking lot? Well, I know that I reach a maximum area when the width is 160 feet. There's no point in me finding out what the output here is because they're not asking for what is the area of the parking lot. They're asking what are the dimensions of this parking lot. Well, the width is 160, and look, in our previous equation right up here, let me highlight it. The length is just 640 minus twice the width. In other words, the length is 640 minus twice that 160. Well, twice 160 is 320. 640 minus 320 is actually 320. So the length in this case is 320. Now let's pretend, I'm going to modify this a little bit. By the way, this is done, but let's modify this, make it a little more challenging. Suppose that we want to actually break this parking lot up into 4 sections that we fence off. So maybe a lot A, a lot B, a lot C, and a lot D. Something like this. So you have the same rectangular shape up against a freeway, but you're going to separate these into 4 sections. So you're using more fencing to fence off these other sections, okay? Notice in the previous picture, we didn't have all those extra all the extra fencing used in those intermediate sections. It doesn't necessarily have to be true that these are all the same width, by the way. These can be different size parking lots. In other words, we could have one lot be sort of larger than the other, okay? Something like that. So let's label our unknowns again. This will be our width, so therefore this length will be w, this length will be w, this length will be w, and this length will be w. And since I'm allowing these to be different sized subsections, I'm just going to call this whole thing a length. Okay? It's because I don't know really what that bit is or what this bit is. That's not important to me. I'm actually asking what's maximum, what's the total area that I can fence off. and the best total area. All right, so I've read the problem, I understand what's going on, I've drawn a picture, I've labeled my unknowns. Let's create some equations. And let me switch to a smaller pen for this. First of all, it's the same problem as previous. We have 640 feet of fencing. So I know that 640 feet has to be used up by that L plus 1, 2, 3, 4, 5 of those W's. And I also know that I want to maximize the area. The formula for area is length times width. Now remember, I'm trying to maximize the area, so I'm going to work with this equation. I just have to get the right-hand side to only involve one variable. So I will solve the top equation for L. Notice this is strangely similar to the last problem, right? But the result will be different. So this tells me the area is going to equal 640 minus 5W times W. And now I want to be able to graph this equation to find out when I get a maximum area. And the best way to do this is to find the horizontal intercepts. So here's the W axis, here's the area axis, and I want to find the horizontal intercepts which occur when A is 0. And I see those occur when W is equal to 0 or when W is equal to 128. And let me just double check that. That's 500 plus another 100 is 600. Yeah, that's right. So that's 128. Halfway in between will be the maximum. In other words, the axis of symmetry. It's at 64. So I know if I let the widths here be 64, that I'll get a maximum area. Now, this question is actually asking, what's the actual maximum area? Okay, well the area is just this formula right here. I know that it's maximized when W is equal to 64, so let's plug in 64 here. 640 minus 5 times 64 times 64. In this case, I will kind of cheat a little bit just by bringing up a calculator. So let's see, I have 640 minus 5 times 64, and I will multiply that result by 64. 20,048. I said 20,048, it's 20,480, and that's square feet. That's how many square feet I can house basically with this type of setup. So we got pretty good mileage out of that problem. 2 problems out of 1. Now finally on to what I find to be the most entertaining styles of problems for quadratic models. And these are basically like revenue problems. You want to know how much money you're making, or profit problems or something like that. So when a business charges $600 for a seminar, it attracts 1,000 people. Each person pays $600. But whenever they start to drop the price, of course more people are going to show up, right? So for each decrease of $20, an additional 100 people will attend the seminar. Let X represent the number of $20 decreases, and let's determine a revenue equation and then maximize that revenue. Now, one thing you'll have to know when you're doing these kinds of problems is that the revenue is equal to the cost times number of items sold. And in this case, the cost would be the cost to the customer, because that's what they're paying me. And the number of items sold would be the number of people going. So let's see. This is how you build these. They're actually not bad once you get used to them. The cost that it normally is for somebody to show up is $600. And for that cost, we normally sell to 1,000 people. But we are going to decrease the cost, and that will increase the number of people. We're going to decrease the cost by sets of $20. In other words, one set of $20 or two sets of $20 or three sets of $20 or four sets of $20. We're doing $20 decreases. And for each decrease, I know we gain 100 people for each of those steps. The X is the number of $20 decreases. So every time we have a $20 decrease, we increase the number of people by 100. This is actually our revenue equation. That's R. And now all we need to do is maximize our money, our revenue. You would think that it would be maximized if we just charged $600 per person and we had 1,000 people, but that's not true. We actually will get more money by dropping the price. So let's see how much more. And again, because this is a quadratic, you can tell that when you multiply this out, you'll get an x squared. So it'll be a quadratic equation that this will graph as a parabola. So all I need to do is find two symmetric points. Halfway in between them will be a vertex. Our input variable is x. Our output variable is the revenue. And as I mentioned in the last two problems, if you have an equation that's already been factored, leave it factored. Take advantage of that. What I'll do is I'll say, okay, well, since it's already factored, let's see what happens when the revenue is 0. I'm going to let the revenue equal 0. In other words, when am I making no money? Obviously, I don't want that to happen, but let's just find out when that happens. Because remember, if the revenue is 0, we're sitting on the x-axis. So really, I'm asking, when are we at the x-axis here? So that's 600 minus 20x times 1,000 plus 100x. Well, two objects multiplied to become 0 implies that either this first object is 0 or the second object is 0. Solving both of these, the left equation will become, let's see, 60, 30, 30. X is equal to 30, or second equation, x is equal to a negative 10. So let me plot those points. This is the first time you're seeing something like this, and so I want you to see what the effect is. So I have an x-intercept at 30, and I have an x-intercept at a negative 10. Remember, these are symmetric points on a parabola, so halfway between these two things should be the vertex, or the axis of symmetry. So the axis of symmetry is at the average of those two numbers. Remember how an average works is you add the two numbers and divide by 2. 30 plus negative 10 is 20, divided by 2 is 10. So the average of those two numbers is 10. So in other words, halfway in between, at x equals 10, we have our vertex. And all we're being asked to do is find a value of x that will maximize revenue. They're not asking me actually how much revenue I'm making. They're saying how many price increases or decreases, how many price decreases must I have in order to make the most money? And I find out that if I let x equal 10, in other words, let the number of $20 decreases be 10, I will make the most amount of money. So the answer to this question is we do 10 price drops. That will maximize our revenue. By the way, just to let you know, 10 price drops of $20 each, that means we're dropping it by $200. So $200 drop, which implies that we're actually charging each person $400. And you might think, man, that's a lot less. And it's true. When you charge only $400, you're losing $200 per person. But remember, for each price drop, we gain 100 people. So we gained 10 sets of 100 people. In other words, we gained 1,000 people. So we're attracting the original 1,000 plus another 1,000, 2,000 people. And if you multiply those two numbers, we will have 8 with 1, 2, 3, 4, 5 zeros, $800,000. It will be our profit, or our revenue, I'm sorry. So $800,000 revenue versus our original revenue, which was 1,000 people at $600 each, $600,000. You see what happened there? We only made $600,000 before. We dropped the price. We're making $800,000. And yes, this does work. Okay, I think that's it for quadratic models and stuff like that. The next lecture that I'll probably put out is just doing some random stuff with quadratics, specifically solving quadratic systems.